Assalamualaikum and salam sejahtera to all of you. Today we will discuss chapter 11, Deformation of Solid. First, I will list all the formulas that will be given in PSPM. There are 4 formulas for this chapter. Stress with symbol sigma. So stress equals to F per A. F is force and A is area. So mean that unit for stress here is Newton per meter squared. Newton per meter squared. Strain we use symbol epsilon, so strain equals to E per L naught. E here is elongation or extension, and L naught here is original length. So it means that no unit for strain. Third equation is Young modulus. Young modulus we use symbol Y. So Y equals to stress per strain. Y equals to sigma per epsilon. So Young modulus substitute formula for stress here. Stress equals to force per area. So F per A divided by strain. Strain is E per L naught. So you get this equation for Young modulus stress per strain, or Young modulus Y also equals to F times L naught divided by AE. And unit for Young modulus here is Newton per meter squared. Newton per meter squared. And the last equation given here is strain energy, or energy stored in a wire. So we use symbol U. U equals to half Fe. Half times force times elongation or extension. So unit for strain energy, for energy you need joule. So we start from number 1. Question number 1. Figure 1 shows a 10 kg weight suspended by 0.2 meter vertically coupled wire with cross-sectional area 5 millimeter squared. 5 millimeter squared. So it means that here is A, area. So area is equals to 5 millimeter squared. So we convert it to SI unit. SI unit is in meter squared. So it means that millimeter here is times 10 power of negative 6 meter squared. And then a 5 kg weight is suspended by a similar wire. So similar wire, so mean that wire 1 and wire 2 here, wire 1 and wire 2 here is similar wires. It means that we have the same Young modulus. Same Young modulus. So for copper wire, Young modulus given here is 1.10 times 10 power of 11 Newton per meter squared. Okay, so a 5 kg weight is suspended by a similar wire from the bottom of the 10 kg weight. Okay, so calculate A, strain of each wire. Strain here is epsilon, so mean that you must calculate epsilon 1 and epsilon 2. Okay, so calculate epsilon 1 and epsilon 2. So refer to this diagram. So from this diagram, we have 2 masses or 2 objects here. So first step, we must draw free body diagram. So mean that we have 2 free body diagram here. We can start from bottom here. mass 5 kg here. So from here, so we have weight. So direction weight, let's say we label as W1, weight 1. So direction weight 1 is downward. So label it W1. And we have copper wire here. So we have tension here. So tension here, direction tension is out from this object. So mean that upward tension 1, so we can label it T1. And so we mean that object 1 here. So we have two forces. We have T1 and weight 1. Okay, so here is free body diagram. First object, T1 upward and weight 1 downward. The second object is here, 10 kg here. So we have weight, direction weight downward. So we can label it weight 2. And here is tension 1 here. So direction tension 1 is out from this object. So mean that direction tension 1 downward. Okay, then we have another wire here. So mean that here is second wire is T2. So direction T2 out from this object. So mean that direction T2 outward. So can label it T2. So here is free body diagram for second object. So direction T2 is outward and T1 and weight 2 downward. So from free body diagram, first free body diagram here, so you can determine T1. And from second free body diagram here, so you can determine T2. Okay, so we refer to first free body diagram here. So the system is at rest, so mean that net force Fy must equal to 0. So mean that T1 equals to weight 1. So weight 1 equals to 5 kg times 9.81. So you can determine T1. So you get T1 equals to 49.05 Newton. And then from second free body diagram here, okay, Fy also equals to 0. So it means that T2 equals to T2 outward equals to T1 plus weight 2. So we can substitute the value. Weight 2 equals to 10 times 9.1. T1 equals to 49.05. So you can determine T2. So we get T2 equals to 147.15 Newton. So now we can calculate strain for each wire here, epsilon 1 and epsilon 2. So we can use equation Young modulus. Okay, so Young modulus equals to stress per strain, right? Stress per strain. So first calculate for first wire 1. So Young modulus equals to stress 1 divided by epsilon 1, strain 1. So stress equals to force per area. So force 1 is T1 here. So T1 per area per A divided by epsilon 1. So we can substitute the value. Young modulus given here is 1.10 times 10 power of 11. And T1 here 49.05 Newton. And A is 5 times 10 power of negative 6 meters squared. Substitute the value. So you can determine epsilon 1. So epsilon 1 is strain for wire 1. So you get answer here. Epsilon 1 equals to 8.92 times 10 power of negative 5. So for strain second wire, so we can use the same equation. Okay, so can use the same equation. Stress Young modulus equal to stress per strain. So stress here is stress 2 and epsilon here is epsilon 2. Okay, so equals to T2 per area divided by epsilon 2. So we substitute the value. So we have the same Young modulus here. So Young modulus equals to 1.10 times power of 11. And T2 is 147.15. And area here is 5 times power of negative 6. Substitute the value. So you can determine epsilon 2. So you get epsilon 2 equals to 2.68 times the power of negative 4. And then for B, calculate the extension for each wire. So it means that calculate E1 and E2. So for E, so you can use equation strain. Okay, because strain, epsilon here, strain equals to E per L naught. Okay, E per L naught. So you can use E per L naught for Y1. So epsilon 1 equals to E1 per L naught. So we can substitute the value E1 from A. L naught is 0.2 meter. This one is L naught 1. And here is L naught 2. So substitute the value. So you can determine E1 here equals to 1.78 times the power of negative 5 meter. Okay. Then we use the same equation to determine E2. So epsilon 2 equals to E2 per L naught. L naught here is L naught 2. So substitute the value E2 from A, and L naught 2 equals to 0.2 meter. So you can determine E2. So we get E2 equals to 5.36 times the power of negative 5 meter. Number 2, a 4 meter iron rod with cross-sectional area 0.5 cm squared extend by 1 millimeter when a 225 kg mass is suspended from one of its ends. So calculate the Young modulus of the rod. So calculate Young modulus Y. So here 4 meter iron rod. So mean that here is L naught. So L naught here equals to 4 meter. And cross-sectional area, so we mean that this one is A. Okay, cross-sectional area is A. So A equals to 0.5 cm squared. So convert to SI unit. So mean that A equals to 0.5 times 10 to the power of negative 4 meter squared. Okay, extend by 1 millimeter. So this one is 1 millimeter. Here is E. Okay, so this one is E. Elongation or extension. E here is 1 millimeter. So 1 millimeter. SI unit is 1 times 10 to the power of negative 3 meter. Okay, from here so we can sketch diagram. So we can sketch diagram here. We have iron rod, and at the end of iron rod here, okay, we have what here? 225 kg mass suspended, okay, from end of this iron rod. So from diagram here, so you can sketch free body diagram. So it means that weight for this object is downward and force here upward. Okay, so we can use F or T. If you want to use F, so label it as force F. So you get free body diagram here. Okay, F upward and weight downward. So from free body diagram here, so we can calculate force F here. So Fy system is at rest, so Fy equal to 0. So it means that F equals to weight. And weight here equals to 225 kg times 9.81. So you get F equals to 2.21 times the power of 3 Newton. So to calculate Young modulus, so you can use equation Young modulus. Okay, Young modulus equation is stress Y equals to stress per strain. Okay, stress per strain, and stress equals to F per A and strain equals to E per L naught. So you get equation Young modulus equals to F L naught divided by AE. So you can substitute the value. F here is 2.21 times power of 3 Newton. L naught is 4 meter. A here 0.5 times power of negative 4 and meter squared, and E here is 1 times power of negative 3 meter. So we substitute the value here. So we can use calculator. So you can determine Y. So you get Y equals to 1.77 times 10 to the power of 11 Newton per meter squared. Okay, now for B, calculate elastic energy stored in the rod. Energy stored in the rod. So mean that calculate what? U. Okay, calculate energy stored or stress energy. Okay, so we use equation U equals to half Fe. Okay, so F is 2.21 times power of 3 Newton and E is 1 times power of negative 3 meter. So substitute value here. So we can use calculator. So you get U equals to 1.105 joule. Number 3, a metal wire X with cross-sectional area of 5 mm squared. Okay, so mean that here is area for wire A. So mean that this one is AX. AX equals to 5 mm squared. So mean that 5 times the power of negative 6 meter squared. Okay, it's stretched by 0.2 millimeter. Okay, so mean that this one is EX, E for wire X. 0.2 millimeter. So times power of negative 3 meter. Okay, by a certain stretching force. So how long will a wire Y? How long will a wire Y of the same metal and length stretch? So mean that calculate EY. So that one calculate EY. Okay, of wire Y of the same metal. So mean that wire X same metal with wire Y. So mean that Young modulus for wire X equals to Young modulus for wire Y. Okay, so Young modulus wire X equals to Young modulus wire Y. And length, okay, so same length, so mean that L naught X equals to L naught Y. Okay, if its cross-sectional area is double, so mean that double of wire X, so mean that cross-sectional area wire Y is 2 times cross-sectional area wire X. While the magnitude or stretching force is the same, so mean that Fx equals to Fy. So Fx equals to Fy. So here we have 3 items here. Okay, have the same value. Okay, Young modulus, L naught, and force. Okay, so now you can use equation Young modulus equation. Y equals to stress per strain. So stress equals to F per A and strain equals to E per L naught. So you can use this equation. So we can rearrange this equation. Okay, so we can arrange this equation. Y per FL naught is equal to 1 per AE. Okay, so mean that this item here, Y, F, and L naught is the same value for wire X and wire Y. So Y per F, L naught equals to 1 per A times E. So we use this equation. Okay. So Y per FL naught wire X is equal to Y per FL naught wire Y. So you can write equation here. Okay, then Y per FL naught is equal to 1 per AE. Okay, so 1 per AE wire X equals to 1 per AE wire Y. Okay, so we can substitute the value here. AX, we can say AX, and AY is 2 times AX. So substitute the value, and EX is 0.2 times power of negative 3 meter, and EY we must calculate EY here. So we substitute the value. AX, okay, so AY here equals to 2 times AX. AX is equal to AX, so mean that you can cancel AX here. Okay, so cancel AX. So we use calculator, so you can determine EY. So you can determine EY here, so you get EY equals to 1 times 10 to the power of negative 4 meter. Okay, number 4, a metal wire of 1.2 millimeter diameter and 3 meter length is stressed by forces, okay, of various magnitude. The stress against strain graph of wire is as shown in figure 4 here. Okay, so here is graph stress against strain. So we get straight line graph here. Okay, so 1, calculate the Young modulus of the metal wire. So we know that equation for Young modulus equals to stress per strain. So y-axis here is stress and x-axis here is strain. So it means that you can calculate Young modulus from gradient for this graph. Okay, from the gradient. So we use equation stress per strain. So gradient, so substitute value. How to determine gradient? Y-axis divided by x-axis, right? So y-axis here 10.5 times power of 7 Newton per meter squared minus here 0. Okay, divide by strain here y-axis, x-axis 1.50 times power of negative 3 minus 0 here. So you can calculate y Young modulus. So you get y equals to 7 times 10 power of 10 Newton per meter squared. And then for 2, what is the applied force if the stress of the wire is 10.5 times power of 7 Newton per meter squared? So what is the applied force? So mean that determine F. Determine F. So A. So you can use equation stress sigma equals to F per A. Okay. So stress here from diagram here, from graph here. Okay, so stress here equals to 10.5 times power of 7 Newton per meter squared. And area, what is area? We given here is diameter. We know that area equals to pi r squared. Pi r squared. So r here, r is half diameter. Okay, so diameter is 1.2 millimeter. So it means that radius is 0.6 millimeter. So millimeter times power of negative 3 squared. So you can determine area. So substitute value. Okay, substitute value here. So you can determine force F. So you get F equals to 118.75 Newton. And then for the question here, determine the strain energy stored in the wire if the strain is 1.5 times power of negative 3. So determine what here? Strain energy. So mean that determine U. Okay, so U we use equation U equals to half F E. F half F E. Okay, F from 2. E, we don't have E here, but we have strain. So you must determine E from strain here. Okay, we know that strain equals to E per L naught. E per L naught. L naught, this one is L naught, original length. So L naught equals to 3 meter. Okay, L naught equals to 3 meter. So first we must determine E. Okay, so we use equation stress equals to E per L naught. So we substitute the value. Strain equals to 1.5 times power of negative 3. L naught is 3 meter. So you can determine E. Okay, so E equals to 4.5 times power of negative 3 meter. And then to determine strain energy, so we use equation U equals to half Fe. So substitute the value. Okay, so you can determine U. So you get U here 0.27 joule. Okay, that's all. Okay, thank you.